Everybody, so this video lesson is going to help explain the calculations involved for lab number 13. And the first thing I want to point out is this data table up here at top. I actually grabbed this from a set of data from a lab group from a number of years ago, but their data was pretty good, so I grabbed it, a little screenshot, and put it on here. First thing I want to talk about is that these absorbance values were all collected using the colorimeter, just like yours were. And these are numbers that they calculated from calculations 1 and calculations 2 in the calculations section of the lab write-up. But these values here, these concentrations and the Kc, are things we need to calculate using this ICE table down here. So I created this ICE table so that our students can just plug in numbers and solve for missing variables. And so you can calculate the initial concentration of the Fe3+ using calculation number 1. You can calculate SCN, concentration initially, with the concentration number 2, or calculation number 2. And initially we have 0 of the product. So I'm just going to erase those quick. We need to figure out how to calculate the changes. The change row is the most important. And in order to do that, we need to basically manipulate the standard. The standard is kind of what everything's going to revolve around here. We need to find this number down here, the FeSCN at equilibrium, in order to calculate the change between 0 and that number, and then apply that change to the other two reactants in this reaction. And in order to do that, what we do is we compare the absorbance values in each trial with the standard. Now Beer's law, if you remember back in the colorimetry lab, talked about how the absorbances are proportional to the concentrations. So if you know the absorbance, you can basically calculate the concentrations. And so what we're doing is setting up a ratio of absorbance for each trial versus the standard. And so we can calculate that. We can figure out the proportion between A1 and A standard and set that equal to the concentration of the FeSCN at equilibrium for trial 1 over the FeSCN for the standard. Now the unknown that we're going to solve for is this variable right here. We can call that x right off the bat. That's going to be the number that we solve for, and then we're going to plug it in to this bottom right hand corner of the ICE table and use that to calculate the change in our reaction. And now I'm going to explain to you how we calculate the FeSCN for the standard. And once we have these, we have the absorbance 1 versus absorbance standard, and then we have the FeSCN for the standard. We can solve for the missing variable. That missing variable will go down here, and then all the dominoes will fall from there. We can calculate the change, apply the changes to the two reactants, do the subtraction, and eventually find the equilibrium concentrations of the Fe, the SCN, and the FeSCN, and calculate then our K. Now in all of these reactions, you have the same reactants, and it's worth noting that in the first 4 test tubes, these were fairly similar in concentration. In fact, you started with the same concentration, 0.001 molar of this, and this stepped up a little bit each time. But in the standard, this number was really, really high. In fact, it was 100 times the concentration of the SCN in the standard. This SCN was its normal concentration, but then this was 100 times the concentration of that. And we haven't gotten into this yet, but there's something that you might remember from last year called the Chatelier's principle, which basically means that you can shift or force equilibrium to create lots and lots of products by increasing the reactants on the left-hand side of the reaction. And by loading up high concentrations of iron here, we actually basically say that for every SCN that was in solution, all of it got converted to FeSCN, essentially dropping this to 0 molarity and boosting this up to the molarity that matches the initial molarity of the SCN initially. So if we know the SCN concentration initially in the standard, we know that it produces FeSCN in equal concentrations for the standard. And then that number gets plugged in right down here. Now, that number will get reused for all of these calculations, and so you'll just simply do A1 over A standard is equal to X over the FESCN standard, and then calculate this number. Then you're going to do the same thing. You're going to erase this and do for trial 2, and you'll use the absorbance for trial 2 versus the standard equals X over the standard concentration. And then you'll do it for number 3, and this time you'll use the third absorbance. And you'll basically generate 4 different values for FESCN at equilibrium. Then you're going to have to do an ICE table for all 4 of your trials from up above. So you do an ICE table for all 4, calculate the KC, which again is the products, which is the FESCN concentration at equilibrium over the Fe times the SCN concentration, and you'll get the Kc value. Hopefully after watching this little video lesson, these calculations are a little bit better explained to you. I've actually posted a copy of the example calculations, basically how I would expect them to be neatly prepared so that they're organized and easy to follow. I've posted the set of calculations that went along with this data table in the Schoology folder. So take a look at those if you would like an idea of how I would expect your calculations to be neatly written, large enough to read. Thanks for listening.